Start. The final seminar of today's session will be given by Hermann Schulz-Baldes from Erlangen, and he will speak about the random phase hypothesis for quasi-one-dimensional random media.
So, thank you very much for the introduction, and thank you very much to all of the organizers for inviting me to this prestigious place, and moreover, give me occasion about the modest mathematical progress that I have made together with Christian Sadel, who is here in the audience, and that has been complemented by numerical work by Rudolf Römer, just about 100 miles from here in Warwick. So it's going to be about, as was already said, a random phase hypothesis. Let's give a quick overview about what I want to tell you. The objects are random Schrödinger operators on a discrete lattice, and moreover on a quasi-one-dimensional strip of finite width L. So samples should look like this here, where this width L is finite, and the length of the sample n is going to be infinite in most of what I say behind. And in particular, we're interested in a weak coupling limit of the randomness and at energies which are inside of the spectrum of the free operator, which is typically the discrete Laplacian on a lattice. Now, aims are that I first of all want to state a correct form of the random phase hypothesis. In the physics literature, this is sometimes also called a maximal entropy ansatz, and I hope I can convince you that there has to be a little bit of care to state what that really means. Then afterwards, I want to provide a general tool which allows to check the validity of such a random phase hypothesis, at least in a perturbative situation of small coupling. And what this actually does, I think, is establish some kind of a link between the random Schrödinger operators and random matrix theories. However, only for quasi-one-dimensional random systems, and not for finite volume approximations of the Anderson model on cubes, for example. However, in this quasi-one-dimensional situation, this link is heavily used, for example, for the derivation of DKMP flow equations, and is in itself interesting, I think. What we are rather going to do is we're rather going to use it in order to derive controlled perturbation theory for the Lyapunov exponents of these systems. And well, towards the end of the talk, I want to talk about matrix-valued Sturm-Liouville oscillation theorem, and I hope to combine it somehow with this random phase hypothesis to make some speculations of what should be true for finite volume operators on cubes. So here once again the operators. So the Hilbert space is L2 of Z with fibers in CL. So each of these vectors, I don't know which bottom this is here. Well, maybe I'll take that one. Each of these vectors here are in C to the L, and the Hamiltonian has discrete Laplacian describing the jumps into the longitudinal direction, and has operators inside of each fiber, which consist of a fixed part, delta, which could be thought of as a magnetic Laplacian, typically, and a random part, lambda Vn, which is coupled by a small coupling constant, real. And inside of the Vn, one can now put various models describing the physics on this strip. So the most conventional one is the Anderson model on a strip, where this Vn is a diagonal matrix which has diagonal entries which are independent, identically distributed and centered. However, another model that I'm going to be interested in is where the Vn's are full random matrices, Hermitian random matrices, with entries having the covariances as stated here. And this is somehow similar to Wigner L orbital models, where all the orbitals inside of one fiber here are randomly coupled. So all the randomness all these Vn's are encoded in one parameter omega here. And I want to point out at the very beginning that we do not need to make any assumption about the distribution of the randomness. In particular, it might have some atoms and be a Bernoulli distribution. So the first thing one usually does when studying these objects is to rewrite these quasi-one-dimensional Schrödinger equation in terms of transfer matrices. And for that, I have here immediately reformulated for matrices. Namely, I don't look at only solutions psi-n which are vectors in CL, but look at matricial solutions. And they satisfy this transfer matrix equation. And Ten is the transfer matrix. And it's important to take note that this is a Hermitian symplectic matrix. So it satisfies for real energies the relation that conserves the symplectic form. And if, moreover, the system has no magnetic field, then the symplectic matrix is a real symplectic matrix on the symplectic group as it's known to everybody in the audience. So the star here is complex conjugate and transpose. And if you have no magnetic field, you may as well put the transpose here. Now, these transfer matrices act on the vectors psi-n, psi-n minus 1. And the way that I want to look at them is that they span Lagrangian subspaces, so spaces of half dimension. Namely, these are matrices here of dimension 2L times L. And if they are Lagrangian, that means that the symplectic forms on them, then the transfer matrices maps one Lagrangian space to a new one. So there's a natural action of the transfer matrices on these Lagrangian spaces. And we want to change coordinates and look at it a little bit different representation by taking conjugation of the symplectic group to a generalized Lorentz group. So that is done by the Cayley transformation. And if you Cayley transform the symplectic form by multiplying it from the left by C star and from the right by C, then you get the Lorentz form of signature LL, and the symplectic group, therefore, is isomorphic to the generalized Lorentz group. And this generalized Lorentz group acts now on isotropic matrices with respect to the Lorentz form. So that's what's written up here. Let us look at this action, and let us look first more precisely on the objects. So the objects are matrices of size 2L by L. They have maximal rank, and one should think of the L vectors as spanning a subspace of an L-dimensional subspace in C to the power 2L. And, well, they are isotropic. Now, two such matrices phi represent the same subspace, maximally isotropic subspace, if I can change coordinates inside of the phi by multiplying from the right with an invertible matrix. And if I use that as an equivalence relation, then the quotient with respect to this equivalence relation of the isotropic matrices gives you the set of maximally isotropic subspaces. The nice thing is that that object is naturally diffeomorphic to the unitary group. Namely, if you take phi in the form A over B, you can check that the B is an invertible matrix, and if I calculate A times B minus 1, the relation of the isotropy tell you that that gives you a unitary matrix. So associated in particular to our solutions, matricial solutions of the Schrödinger equation, I have associated unitaries by taking the solution, Cayley transforming it, and then doing this so-called stereographic projection, and therefore you get a sequence of unitaries. And the action on the Lagrangian subspaces by the transfer matrices, or more general by any matrices in the Lorentz group, is implemented by Möbius transformation. So if I have any matrix A, B, C, D in ULL, this Lorentz group, it acts on UL by the usual formula, where this inverse here is a matrix inverse now and exists, and the formula gives you again a unitary matrix. So for the case L equal to 1, this is something that many of you know very well. Namely, the unitaries are simply prefer phases, and the transformation that with the Möbius transformation is the usual transformation of prefer phases. In physics literature, quite often these objects are also called the Dyson-Schmidt variables. Good. Now what do we have? We have now associated to our random operator a random sequence of transfer matrices, and therefore a Markov process on the unitary group by successively applying the random transfer matrices. And well, this is a Markov process on UL. And the use of this Markov process is that many interesting quantities, both mathematically and physically interesting quantities, can be calculated from this process. So as an example, and moreover, I should say they can be calculated as Birkhoff sums of this process. So as an example, let's look at the Lyapunov exponents for a quasi-one-dimensional system. So there are L of them, and if I take the average Lyapunov exponent, and denoted by L gamma of E, and look at the integrated density of states of such a quasi-one-dimensional system, they form a Herglotz pair, and I can calculate both of them together as a Birkhoff sum of some function f of E, well, which I've written out here, but let's not look too close at that. It's a smooth function, and the important thing is that we are interested in looking at these Birkhoff sums of such a smooth function on the unitary group here. Now, what would be nice is, of course, to know the distribution of these unitaries, and a rough version of a random phase hypothesis could be to say that these unitaries are simply distributed according to the Haar measure. Now, if they're distributed to the Haar measure, then of course I can calculate the Birkhoff sums of any function quite easily by just integrating over the unitary group. And well, I can calculate then very easily, for example, Lyapunov exponent density of states. Now, that's a bit naive. There are two reasons which I want to explain. Namely, they are so-called hyperbolic or closed channels, and moreover, one should take care of the orientation of the unitaries such that one may have here a Haar distribution. So, moreover, the statements that we're going to have afterwards is that such a refined version of the random phase hypothesis is only going to be true in the situation of weak coupling, so for small randomness. So if we want to do perturbation theory, of course, what we should do is have a very good understanding of the free dynamics of our system. So what happens without disorder, and what one can do in order to analyze that is to factorize the transfer matrix into a part which doesn't contain the disorder, plus a remainder, which I wrote as such, and then first of all do a symplectic diagonalization of the free transfer matrix. So this diagonalization, let's call it M, is a symplectic matrix, and it transforms this free part into a rotation matrix, which is of the following form, which is not the most general form, but well, quite often of this form, where first of all you have a so-called hyperbolic channel composed of these two blocks here, which are LH times LH blocks with diagonal entries given by an exponential of a diagonal and positive matrix. And LH is the number of hyperbolic channels. And then you have elliptic channels, well, which can be written by a standard rotation matrix, which also is diagonal. I mean, each block here is a diagonal matrix. And the sum of the two, the number of elliptic channels, LE, and the hyperbolic channels should be the full number of channels that the system has. Now, of course, in general, one may also have Jordan blocks, and they do arise at special energies in the system and correspond to internal band edges, but let's neglect these for the first time. Now, of course, if I do this transformation, I diagonalize the free parts through this R, and something happens to the remainder, and you just calculate. It gives you a random Lie algebra element which is whatever it is. You can calculate it explicitly. Good. Now, let's look at the modified or M-modified matrix proof-phases. So matrix proof-phases are these unitaries, but now in this new system of, in this new representation under M. And then we can state a refined random phase hypothesis as follows. At weak coupling, so for small randomness, for small lambda, these M-modified proof-phases are, first of all, fixed in hyperbolic channels and hard distributed on the elliptic channels. Now, that's a statement which can numerically be checked. For example, for a magnetic Anderson model on a strip for small coupling constant. And indeed, what one finds is that the hyperbolic part, the U's, these matrix proof-phases, they are fixed on the projection on the hyperbolic part of our system, and they're actually in the choice of gauge, in the choice of the matrix M stated before equal to 1 there. And the elliptic eigenphases, well, first of all, one can look at their density of states, and it's flat, which is one indication for having a hard distribution. And moreover, one can look at their statistics, and depending on whether the Anderson model has a magnetic phase, has a magnetic term or not, the statistics of these eigenphases is either GOE or GUE, of only the elliptic ones. You exclude first the hyperbolic ones, you look only at the elliptic ones. Good. Now, before going on, let me say that in order to calculate other quantities than the average Lyapunov exponent in the density of states, as for example, if one, for example, is interested in calculating all of the Lyapunov exponents, one has to look at a larger object, not just these matrix proof-phases, but at the whole flag manifold, which can be calculated by taking the quotient of these isotropic matrices with respect to a difference equivalence relation where you allow basis changes only with upper triangular matrices. But again, the quotient is a nice homogeneous space and has a natural action of, again, the unitary, the Lorentz group, ULL. And again, one has a Haar measure on there, and again, one can formulate a random phase hypothesis and can check it. So now I come to a more abstract approach in order to check some kind of a random phase hypothesis. So let's suppose that we have a random sequence of elements in a Lie group, which are of the following form. They have a 0th order term and a perturbative term, and only the perturbative term is random and has a small coupling constant. And let's suppose also that the non-random term here generates a compact subgroup. So what I do from the very beginning now is that I exclude the hyperbolic channels and restrict myself onto that part which where one should actually have a Haar distribution. Actually, it's not so difficult also mathematically to exclude these hyperbolic channels. And this is the harder part. Now, the P's here, the P sigmas are independent identically distributed elements in the Lie algebra, which are centered. And we also suppose that this group acts on a compact homogeneous space, which again I denote F for flag manifold, on which we have nice Riemannian volume mu. Now, again, we have then an induced Markov process on this compact manifold, and we're interested in the perturbative calculation of Birkhoff, averaged Birkhoff sums along the orbits of this random dynamical system. Now, what is known before starting to do any calculations is operator ergodic theorem of Dunford and Schwarz, and it states that the limit as n goes to infinity of such sums even exists almost surely. However, with respect to any invariant measure of the Markov process, and there might be many invariant measures, and therefore it doesn't tell you a whole lot about the value of these Birkhoff sums. More particular situation, one has Furstenberg uniqueness results. So if one has all the setup coming from theory of products of random matrices as in the motivation, then one knows under certain conditions that there's a unique invariant measure, and one also knows that this invariant measure has certain continuity properties. Typically, it's a Hölder continuous measure. But what one particularly does not know is whether this measure is an absolutely continuous measure. That's a nice property that one sees in numerics, for example, and one would like to prove. So our statement is that, at least in a perturbative sense, these Birkhoff sums here are, can be calculated using a perturbative invariant measure which is absolutely continuous with respect to the Riemannian volume. The density is rho, and you can do this calculation, well, for certain functions f, as I'm going to explain, up to error terms. The error terms are small in the coupling constant and decrease as you take an average of a longer and longer sequences of the process. Now, one thing to point out at the very beginning is that here what we do obtain is that at least in a weak limit, the invariant measure is unique and that it is absolutely continuous. Yeah? Because, I mean, at least this mu rho here is an absolutely continuous measure. And in order to get something like this, of course, one should have some kind of a coupling hypothesis, just as one has for Markov chains on discrete spaces, for example. So here's our coupling hypothesis. We look at the support of all the random Lie algebra elements and rotate it with the lowest order term, namely the rotation, as much as we like. So this R here is the group generated by the original rotation, and then you rotate all the elements in the support. You already get a rather large set, and then you take the Lie algebra closure of that, which might be a huge Lie algebra, even if the support of your random elements at the beginning was very small. Now, the hypothesis is it's sufficiently large to contain the Lie algebra of a transitively acting subgroup U, transitively acting on the compact manifold F. And, well, then the statement below here holds for not all functions. Well, it holds under two conditions. Either the function F consists only of low frequencies, and I'm going to explain what that means in a second, but in many applications one has functions of low frequencies, or the rotation is a Diophantine rotation. So let's explain these two last hypotheses standing there. So the group, yes?
About the previous slide. So is the, you know how the error term depends on the width of the system, the L which you have on the...
It doesn't depend on the L of the system. It does depend on the derivative, on the second derivative of the function f. But the whole point is that we want to do it independent of L. Now, let's explain the last two notions here. So, well, the group generated by R is a compact abelian group, and therefore we have an isomorphism to a torus times a cyclic subgroup. And, well, if you look at the map, which maps an element out of that group onto the function R applied to U, we ask that this is a finite has finite Fourier series whenever the function is called, well, to consist of only low frequencies, uniformly in U. And the second thing was that, well, this Diophantine condition means that if inside of this group the original element R is represented by one theta under the isomorphism, then this theta should be a multidimensional Diophantine angle, and the technical condition is written here. So I think I said this, but let me go back once and comment what I said, what was there on the last slide below, that this condition here somehow should be understood as a Lie algebra version of the Fürstenberg irreducibility condition. And is an adequate, I think, an adequate coupling hypothesis to make. Now, let's very, very roughly give very, very rough idea only of the proof. And in order to do that, I want to focus on the case where R is equal to 1. So the dynamics is really only given by very small kicks and it's not superposed by this rotation to the lowest order. And what one can think is that, well, we have a discrete time Markov process with small steps. If I take the limit of small steps, somehow in the limit of very small steps, I should be able to see diffusion process behind the which describes the process at least approximately. And the generator of this diffusion process is what we're going to work with and which we're going to analyze. So now a little bit more technical. For every Lie algebra element P, there's associated a natural vector field on the compact manifold by this formula here. I denoted delta P. And let's consider, well, we have these random Lie algebra elements. Take the square of these vector fields and then take the average and consider the operator L defined by that. Now that operator L appears naturally if you make a Taylor expansion of the Markov generator. Markov generator is what I wrote here, where F is a smooth function on the manifold. You let act the random matrix element, I mean the random Lie group element, and take the expectation. Now expanding that leads to, first of all, f of u, because r is supposed to be equal to 1. And then the term in lambda vanishes because we suppose that that the perturbation is centered, and the second order term has this Markov generator inside of it. And then you have third order terms which are just bounded by the derivative of the function f. Now, taking Birkhoff sums of the two sides of this equation lead to the following, that the Birkhoff sum of these objects and of these objects here are actually equal up to boundary terms. So what we have is that the Birkhoff sum of this L of f is given, well, by lambda cubed. If I divide it by lambda squared, I get a term of order lambda. And there are the boundary terms, which of course also have to be taken care of, but they decrease as 1 over n. So these are the Birkhoff sums of images of the operator L. Now, this operator L has an adjoint in the L2 space with respect to the volume, and that operator is also a second order differential operator, which is of the Fokker-Planck type. And main claim is now that the kernel of that operator here is one-dimensional and spanned by a smooth density rho, which can be normalized and is positive, and that moreover the space of all smooth functions on the manifold is given by a direct sum of the constant functions and the image of this operator L. So once you know that, this main claim, then the theorem follows readily, because any function f, of which I want to calculate the Birkhoff sum, is given by a constant function, which turns out to be the constant function times this integral, which appears in the theorem, plus something which is in the image of the operator L, and that is small, and that's the remainder term. So the main thing are these two claims here. Now, I'm not going to say a whole lot about their proof, but the important thing is that you can bring the operator in a Hermann form, namely write it as a sum of squares of vector fields, a finite sum of squares of vector fields, and then the main hypothesis, this Lie algebra hypothesis that I stated, implies that the operator L and its adjoint are Hermann operators in the sense that these vector fields span at every point the whole tangent space if you only take the Lie algebra closure. And then you have available full technology of Hermann operators, and particularly hyperellipticity, subelliptic estimates, and there's a maximum principle for these operators which states that you have a unique ground state. And final thing that one has to check, which is a bit tricky calculation, that these operators are dissipative, and then you can look in Brian Davies' book and have more functional analytic information which allows to conclude the proof. Now, one thing along the lines is that what we saw is that the kernel here of the L stars is one-dimensional. Now, imagine that I have found, I can check that for some reason the constant function on the manifold is in the kernel. Then I've actually determined the kernel, and I can conclude that the perturbative invariant measure is indeed the Haar measure, and that's what we called random phase, that the random phase hypothesis holds. So that's a nice way to check that. Now, actually, in the case r equal to 1, you can iterate the above procedure and get a whole expansion of the Birkhoff sums in lambda, but unfortunately, we can't sum up this whole expansion because the error terms here depend on higher and higher derivatives of f and cannot be controlled. Also for analytic functions f. Up to now, we were not able to do that. Now, if r is not equal to 1, one has to work more, and but under this Diophantine condition, it can be checked that it's possible to replace the generator L by a new generator, which is basically obtained by averaging over the whole group generated by the lowest order rotation R. Good. So now here's some implications. Let's look first at this Wegener L orbital model that I had stated at the beginning, and suppose that the discrete Laplacian in there is 0. Then for energies which are away from the band edges and the band center, one can apply the corollary and indeed check that the perturbative invariant measure on the full flag manifold is the Haar measure. That's not at all a trivial fact, even though one supposes that in all fibers one has already a random matrix. So actually what one has is one has somehow an intermediate model between a random matrix model and a Schrödinger operator. And in this situation, the random phase hypothesis as stated hold. And well, some applications of that is where actually you don't need the full force of this, is that you can calculate the whole Lyapunov spectrum. And it turns out that the Lyapunov spectrum is equidistant, and that we can control the errors quite well. And this Lyapunov spectrum, however, is considerably larger as in the Anderson model. So, for example, if you look at the sum of the Lyapunov exponents, it behaves as lambda squared times L squared here. And this L squared should be understood as the number of random entries in each fiber, which here is L squared, which is of order L squared, which is much larger than in the Anderson model. Now, let's come to the band edges and the band center. So, first of all, at the band center, one has a Kapos Wegener anomaly. And if one looks at the L orbital model, again, as I stated before, one can once again check this random phase hypothesis. And one can again check that the hypothesis of the theorem holds, but the random phase hypothesis doesn't hold. So the invariant measure is the perturbative invariant measure is not the Haar measure, but it is something which has a smooth density rho, which in particular cases again one can calculate, and therefore we can again get a controlled perturbation theory for the sum of the Lyapunov exponents, for example. And again, it behaves as lambda squared times L squared with a coefficient that we can calculate and errors that we can estimate quite well. Now, at the band edges, it was already known. So, for example, band edge E equal to 2, and let's restrict ourselves to the strictly one-dimensional model. It was already known by work of Derrida and Gardner that the Lyapunov exponent scales differently. Namely, it doesn't scale as lambda squared, but it scales as lambda to the power 2/3. And by a refined version of the theorem before, we could prove a rigorous statement that make more or less their claims rigorous, moreover control, moreover correct the coefficient that was not quite right in that theorem, and obtain this theorem about the scaling of the Lyapunov exponent at the band edges. So let's turn to the Anderson model on the strip, so not this Wegener L orbital model. So we only have disorder on the sides, only L values of the potential at the lattice sides, and the operator delta is not 0 here, but it's a one-dimensional discrete Schrödinger operator, so this is the most standard model. First thing that I want to do is I want to define some quasi-momenta, eta k. So you look at the spectrum of this transverse Laplacian. It's given by 2 cosine 2 pi k divided by L, where k just runs through the integer numbers. And subtract energy, and whenever this expression is less than 2, you can define a quasi-momentum, eta k, by this formula. And those k for which it happens are actually the elliptic channels of your system. And now the statement of the theorem is that if I'm interested in the calculation of the localization length, so the smallest Lyapunov exponents, we have a perturbative formula which to lowest order tells us it's of order lambda squared divided by L times a coefficient, which again we can express in terms of these frequencies, I mean these quasi-momentum, and Markov matrix rho KL with positive entries indexed by all of the elliptic channels. So the hyperbolic channels are automatically frozen out and don't play any role in the lowest order contribution to this formula. And well, this is the formula that you obtain, but the error estimates are very bad. I stated here, well, they are, the important thing, they're of order lambda 3, but actually how it depends on the width and on the location of the energy is very badly controlled. To point out the difference between the prior formula in this Wegener L orbital model, actually the smallest Lyapunov exponent was by a factor L larger, as I stated, because there's simply more randomness in each fiber. But this kind of a scaling, lambda squared divided by L, was already expected in an early paper by Tholis. So what one can do with this formula is at least check it numerically again. I mean, let's not worry about the bad error estimate and compare this first term here with the true value for the smallest Lyapunov exponent. And well, the first thing to do is to calculate this matrix rho KL, and actually that's where the computer needs to help us. We know that it's a Markov matrix, but moreover, some kind of random phase hypothesis, or not some kind, the precise random phase hypothesis as stated before holds again, saying that this matrix here is more or less 1 over the number squared of the elliptic channels, so it's constant, as it would be if one has random phase hypothesis. So that's a numerical fact. And hence one can write the smallest Lyapunov exponent in an even simpler form, as it's stated here, and then compare this function as a function of energy with the values for the Lyapunov exponent calculated numerically. So here this is done for 3 different values of lambda. And what you see is that, well, first of all, the lines here have a spiky structure, and that on this spiky structure, which is given by this formula, the actual values of the Lyapunov exponent fall quite well. Now the spikes are precisely those energies at which one has internal band edge, namely that in the normal form of the transfer matrix to lowest order, one has a Jordan block, and at those energies, already the error estimate here breaks down very badly. This is the distance of the energy to these internal band edges enters as 1 over d squared in the estimate. Good. And, well, you can't have a good agreement of that formula for arbitrary large values of lambda, even though quite large values of lambda. Actually, the agreement breaks down as soon as the system passes from a quasi one-dimensional regime to a two-dimensional regime. A two-dimensional regime meaning that the localization length becomes smaller than the width of the sample. So the function would be localized somewhere inside, and then the agreement breaks completely down.
Can you go back to your remainder?
This one?
Yes. Do you remember correctly that last time I heard you talking about that it was different?
No, I don't think so.
In other words, was it not L to the power 3?
No.
It was always L to the power 5?
I think so, yes.
Yeah? Okay, good.
But okay, I mean, I'm not going to make any claims. This is a very bad estimate.
I know.
Yeah, this is a very bad estimate. But
Yeah.
That's not the point, I think. Not yet. I want to improve it, but I cannot.
Yeah, you promised to improve it, and I wondered whether it was better or worse. Okay. I thought it was better, but I'm...
Okay, well, it hasn't gotten better yet, okay? That much I can say.
Definitely. Okay.
So let's come to this finite volume situation where I want to present, first of all, a theorem which I like, which is this matrix-valued oscillation theorem. So it always works when one has a sample of this kind and the Hamiltonian is in a block triangle form. And what one does then is that one starts with a left boundary condition of some unitary, which you just set equal to 1. That represents the Dirichlet boundary condition on the left boundary here. And then you calculate the unitary, the matrix preface as introduced before, on the right boundary. And well, the eigenvalue calculation can be done using this unitary. Now, of course, this unitary has its spectrum on the unit circle. So there are some eigenvalues. And what one can do, so there are L of them, what one can do is that one can look at those eigenphases as a function of energy, and then it's a statement that you can lift them to real-valued functions which are real analytic in the energy. In particular, you might have level crossings of these eigenphases, and you can always choose analytic branches for both of them, or several of them. Now, what comes out of the setup is that an energy is an eigenvalue of the Hamiltonian of multiplicity m, exactly when m of the eigenphases are at the value pi modulo 2. And well, so that's, as I said, it's just coming out of the setup. The main interesting statement is that these eigenphases, as a function of energy, all rotate in the same direction. So they all rotate in the positive sense, some faster, some slower. And a bit more holds, namely, if I look at the derivative of u with respect to energy and multiplied by u star, divide by I, then this is a positive matrix. And if I take that's what one has to prove, and what one can prove. And if I take expectation values of this positive matrix with respect to the eigenvectors of u, I get the phase speeds of these phases here. And each of them is therefore increasing in energy. A little bit more even can be said. Each of those eigenphases, these analytic eigenphases makes exactly n terms. And as I have L of them, I have n terms for each of them. So each comes by the value pi n times. So I recover exactly n times L eigenvalues as I should. Moreover, what one can do is one can implement symmetries in this situation. If the Hamiltonian is real, for example, then these unitaries are symmetric and the positive matrices S are real, have real entries. Good. Now, this is a different way of doing the eigenvalue calculation. In some sense, one reduces the dimension by 1 because, I only need to diagonalize the unitary matrices in order to do it. But however, I have some price to pay. I have to do it for several energies. So I'm not sure if this is numerically interesting, but it's a nice statement anyway. So let me conclude with some speculations. Skip that. And tell you about some preliminary numerical facts that can be obtained for an Anderson model, either on large squares or on large cubes. So L is equal, the width is either equal to n, and I have a square, or L is equal to n cubed if I have a third direction in there. First thing is that there is already a separation of elliptic and hyperbolic channels after going from the left boundary to the right boundary of your sample. So you can split those already in this finite volume situation. However, the random phase hypothesis for these U's doesn't hold in the sense that they are definitely not distributed according to the Haar measure. You simply estimate how much randomness you have put into your system. You realize that actually you only cover a very small portion of the unitary group by this process. So in particular, if you look at the density of these phases, only of the elliptic phases, they are not flat. On the other hand, if you look at the level statistics of these elliptic phases, they are already, well, GOE or GUE, depending on whether it's a magnetic field or not. So this happens both in a metallic phase and a localized phase. And if you want to understand what distinguishes these two phases in this picture, one has to look at the matrices, these positive matrices S. So in the localized phase, if you have a strong disorder, they have a density of states which has fat tails, similar as one has in a quasi-one-dimensional situation. And if one is in a metallic phase, they are approximately given by, I mean, their density of states is approximately given by a Pastur-Marchenko distribution. And what one also can find numerically is that the eigenbases of the unitaries and the phases, they seem to be little correlated. I mean, they're independent of each other. So what's the scenario now for localized phase? You have these high speeds which cause the eigenvalues to move very rapidly and make a full turn, more or less at random energies. And the position of the eigenphase plays no role for the calculation of the spectrum, so the passage of the Hamiltonian, so the passage at the energy minus, at the value minus pi. So basically, these fat tails cause Poisson statistics for the Hamiltonian that you started out with. However, in the metallic phase, the phases move much smaller and have a moderate speed, so it looks like the level spacing of the unitaries, the matrix prefer phases, moves slowly by this value pi here, and therefore leads to the GOE level spacing for the Hamiltonian. So I think all these are numerical facts. Whether they are of any help for understanding the problem on a mathematical level, this I don't know yet. So thank you very much.
Is again open for discussion.
So what's the obstruction to these error terms that you don't like? What's the problem mathematically, let's say?
Well, if, for example, for the calculation of the smallest Lyapunov exponent, the argument that I've done up to now is just using this rotation argument of Pastur and Figotin, and there are small denominators appearing, which basically lead to this 1 over d, which is which appeared in the error estimate, 1 over d squared. And moreover, the linear algebra, of course, for the calculation of the Lyapunov exponent becomes quite involved, and controlling the linear algebra leads to the bad error estimates in L that Ilya was wondering about. Doesn't mean that I think that one should be able to do better, but I'm not up to now.
Is there the systematic perturbation theory then is obstructed by the small denominators or what?
If you approach it in this way, I think yes. I mean, one has to understand better why these small denominators are smeared out by the random potential. And these two techniques haven't been combined yet in order to get the better estimates.
You mentioned the Kaplus-Wegener anomaly at zero energy. So at exactly zero energy, in that case, you don't get the Haar measure, but different. I wondered, so if I go away from zero energy, that changes. Do you understand what the scale is? There must be, so that on the energy axis, there must be some characteristic energy beyond which the anomaly at zero energy somehow decays.
Well, I mean,
do you understand this? How this?
the only thing that can be done, and the only thing that we have done, is to look at, in an energy disorder diagram, what happens at this energy zero when you approach it in different ways. Namely, if you take different exponents, and you actually can reproduce a rich scaling diagram getting always different functions rho, if you take different approaches approach the zero energy in different ways in this phase diagram. And then indeed, as if I take the exponent larger and larger, so come in more and more flat, the function rho converges to the Lebesgue density. But somehow there's a discontinuity at that point, I think. Now, this kind of diagrams can also be obtained at the band edges.
Yeah, so the question was really, how does this, so there's some scaling, lambda versus E, that controls controls the situation. So maybe we can discuss this, how to make this quantitative. John?
If I follow correctly, you seem to suggest that the criterion for the breakdown of the random phase hypothesis for these matrices would be that the width of the system that you've drawn on the board would be when the width of the system becomes bigger than the localization length.
It's even worse than that.
Yeah, I wanted to say that it's much more severe.
It's much worse than that because, well, if you only have a small system, so small n, say, there's no way that if you start with one unitary here and you let act the randomness up to here, you've recovered something which is fully hard distributed at short distances. So this full random phase hypothesis is something which really only holds in the quasi-one-dimensional regime where you have very long samples.
Okay, but then I want to say that even when you go to the limit of indefinitely long samples, it breaks down when you make the width wider. And probably the simplest case to think about is 3 dimensions, I mean 2 transverse dimensions, and then this long dimension and weak disorder so that you're in the metal. So you might hope that with weak disorder and a very long sample, the random phase hypothesis would hold. But I think you can argue that it doesn't. And the point is that you can consider the reflection matrix from one end of the sample, and that's constructed from this unitary matrix. And if you think about reflection from a semi-infinite diffusive system, then there's plenty of spatial structure there. If you inject a particle at one point, then you have some spatial dependence of the probability for it to come out. And you can't recover that kind of structure if these matrices are distributed with the Haar measure. So I think even in a diffusive system, even if the length is infinite, you never get to the
independence of
Haar
L,
measure.
you think? Yeah.
Can I ask a very silly and a general question? Why is it actually important that whether this hypothesis holds or not? What is the why it important?
Well, our physics colleagues use it all the time.
Because okay, that is a good answer. Yeah.
Well, I mean, on the other, also, it's nice to see that somehow an invariant ensemble comes out of the Schrödinger operators. I think somehow it's nice to see that an invariant ensemble, like a Haar measure, comes out of the random Schrödinger operator. Well, here it doesn't come in the way that you expect it, but...
No, but Hermann, when you take your parameter equal to 0, there is nothing to see. I'm sorry. It is clear what is happening there. I mean, of course it is hard, but no, well, where it has to be Haar, it is Haar, and it doesn't. There is nothing to be seen.
Oh.
But if they use it, no, then of course, yes. So.
Any more serious questions or comments?